known as stereoisomerism. Before we start, please like, share, and subscribe to Chemistry Support for more videos. Let's start. Stereoisomerism is a type of isomerism in which compounds possess the same molecular formula and the same structural formula, but differ in the spatial arrangement of atoms. This means that the connectivity of atoms remains the same, but their three-dimensional orientation changes. Because of this spatial difference, compounds may show different physical, chemical, and biological properties. Stereoisomerism is mainly divided into two types. First, geometrical isomerism. Second, optical isomerism. Geometrical isomerism. Geometrical isomerism arises due to restricted rotation around a carbon-carbon double bond. In compounds containing a carbon-carbon double bond, free rotation is not possible because of the presence of a pi bond. For geometrical isomerism, two conditions are necessary. First, the compound must contain a double bond. Second, each carbon atom of the double bond must have two different groups attached. Now let us discuss the most important example, but-2-ene. This compound exists in two geometrical forms. First, cis-2-butene. In the cis isomer, similar groups are present on the same side of the double bond. In this example, both methyl groups, CH3 groups, are on the same side. Due to this arrangement, steric repulsion increases and the molecule becomes less stable. The cis isomer is generally more polar because the dipole moments add together. Now the second form is trans-2-butene. In the trans isomer, similar groups are present on opposite sides of the double bond. Here, the CH3 groups lie opposite to each other. Because of this arrangement, steric hindrance decreases and stability increases. The dipole moments cancel each other, therefore, the trans isomer becomes less polar. This is why the trans isomer is usually more stable than the cis isomer. Maleic acid and fumaric acid. Now let us discuss another important example. Maleic acid and fumaric acid. Maleic acid is the cis form. In maleic acid, both COOH groups are present on the same side of the double bond. Due to the close arrangement of the carboxyl groups, intramolecular hydrogen bonding becomes possible. Therefore, maleic acid is less stable and more acidic. On the other hand, fumaric acid is the trans form. In fumaric acid, the COOH groups are opposite to each other. This arrangement reduces repulsion and increases stability. Therefore, fumaric acid is more stable than maleic acid. Optical isomerism. Now let us move toward optical isomerism. Optical isomerism arises due to the presence of a chiral carbon atom. A carbon atom attached to four different groups is called a chiral carbon. Now let us take the example of lactic acid. In lactic acid, the central carbon atom is attached with CH3, OH, COOH, and hydrogen. Since all four groups are different, the carbon becomes chiral. This gives rise to optical isomerism. If I place the structural formula of lactic acid here and then place a mirror in front of it, its non-superimposable mirror image will be formed. These non-superimposable mirror images are called enantiomers, or optical isomers of each other. One form rotates plane polarized light clockwise and is called dextrorotatory, while the other rotates it anticlockwise and is called levorotatory. So we define enantiomers as stereoisomers that are non-superimposable mirror images of each other are called optical isomers or enantiomers. These two forms are chemically identical under ordinary conditions, but they behave differently toward polarized light and biological systems. Example, 2-butanol. Now let us take another example, 2-butanol. Look at this structure. Its second carbon atom is attached to four different groups. Therefore, it also exists as two enantiomeric forms. The first one is dextrorotatory and the second one is levorotatory. Meso compounds. Now let us discuss meso compounds. Some compounds contain two or more chiral carbons, but they are still optically inactive due to the presence of an internal plane of symmetry. For example, tartaric acid. Now look at the possible enantiomers of tartaric acid. The first structure contains 2 chiral carbons. If I place a mirror beside it, the next mirror image structure is obtained. This structure is a non-superimposable mirror image of the first one. It also contains 2 chiral carbons. Now, if I rotate carbon number 2 along its axis, a third possible structure is obtained. Now look carefully at this third structure. It also has 2 chiral carbons. If I divide this structure from the center, it will be divided into 2 identical halves. This means that there is a plane of symmetry in this compound. If a compound has a plane of symmetry, then it will be optically inactive, although it contains 2 chiral carbons. These types of compounds are called Meso compounds. Now if we name these, the first one is dextrotartaric acid, the second one is levotartaric acid, and the third one is mesotartaric acid. Racemic mixtures. Now let us discuss racemic mixtures. A racemic mixture contains 50% dextrorotatory enantiomer and 50% levorotatory enantiomer. For example, 50% dextrolactic acid and 50% levolactic acid. Since one rotates slight clockwise and the other rotates it anticlockwise by equal magnitude, the net optical rotation becomes 0. This cancellation is called external compensation. Therefore, racemic mixtures are optically inactive, even though they contain optically active molecules.